Speed of light for me and you. Speed of light, lambda nu. Lambda nu. So what we know is that light energy, right, has all these different forms ranging from radio waves all the way down to gamma rays. And the frequency and the wavelength changes, and that associates or correlates to energy. And energy we relate to electron, kind of the distance from the nucleus. And there's theory called quantum mechanical model that kind of bases the idea that every electron has its own unique position when we compare electrons in one element to another, that we call their quantum value, the energy needed to get it to the next energy state. And this ties together electron theory with what we know about waveforms. So speed of light is equal to lambda nu. C equals lambda nu. So when we look at what lambda means wavelength, how long the waves are from crest to crest, right? We see the waves are longer in the red than they are for the blue, and that's true about red light versus blue light in the visible light spectrum. Well, what we also see is that there's a frequency difference, right? The blue light waves are more frequent in some amount of time, maybe this is 1 second, right? We see more waves pass by, more frequent than the red waves. So there's a way to correlate and relate this. So what we're going to do is we're going to do it sort of mathematically. And what we've already sort of looked at is this idea, right? We have all these different waveforms of energy ranging from radio wave all the way down to gamma ray. And they vary in wavelength from long, right, down to short. And they vary in frequency from low frequency up to high. And our frequency values, when we look at them, there's a, factor of 10, right? An order of magnitude. Some people would like to say that. When the factor of 10 or order of magnitude is low, right? We got low frequency, that means less waves. When the order of magnitude's high, 10 to the 20, much bigger than 10 to the 4, right? We got high frequency. Likewise, we could compare lengths of waves with order of magnitude or factors of 10 again, exponents of 10. Very tiny, right? Wavelength, right? Distance from here to here, not a very great distance. So much longer when we get to radio waves. Okay, let's get down to the relationship from the mathematical perspective. So from the mathematical perspective, there is a formula. Speed of light for me and you, speed of light, lambda nu. So here it is, speed of light is a constant, right? The constant is represented by c. C is really just a variable that doesn't change, so 3 times 10 to the 8. So anytime that we're solving a frequency wavelength style relationship, we'll always plug in speed of light. In a vacuum, all light forms travel at the same speed, which means they're not encountering other things that they have to bounce off of, like particles. So first example, blue color light from the sky is a result of scattering of sunlight by the air molecules. The blue light frequency is about 7.5 times 10 to the 14 hertz. Calculate its wavelength in meters associated with this. So we set up lambda nu, speed of light, substitute in speed of light, which is 3 times 10 to the 8th power. So that's all we did here was we took 3 times 10 to the 8 and we substituted it in right there for C, right? Here it is. Then we said lambda, which is what we're calculating, right? Lambda is wavelength. We're going to multiply lambda times nu, which they gave us, right? The frequency is 7.5 times 10 to the 14. So we want to solve for lambda, isolate lambda. So that means we're going to divide each side by 7.5 times 10 to the 14. Well, why would we do that? Because that cancels that, and it leaves lambda alone on the right side. And if we just divide our 3 times 10 to the 8 by 7.5 times 10 to the 14, we end up with a waveform with a length of 4 times 10 to the minus 7. So our wavelength, right, or our lambda, 4 times 10 to the minus 7 in meters. Second example, very similar style calculation. Now they want to know what is the frequency of a wave if we've given you the length. So it's still C equals lambda nu. right? We plug in for the c, the constant, speed of light. We then divide each side by 6.25 times 10 to the minus 9, because in this case, we want to solve for frequency, which is nu, right? This representation right here, v, kind of looks like a v. It's a Greek letter. That's the Greek letter nu. So divide each side by 6.25 times 10 to the minus 9. That'll cancel. That'll leave nu by itself. And now we know nu has a frequency. Now we have the wrong unit of measure here. This is not a frequency unit. Frequency unit would be Hz, hertz. Has to do with how many times the waveform passes in a moment of time, right? So our frequency, 4.8 times 10 to the 16 hertz. Okay, let's take a look at a couple other examples. So we got a C equals lambda nu style problem. In this case, it asks what's the waveform length of a form of radiation with a frequency of 9.75 times 10 to the 8 hertz. Again, C equals lambda nu, right? They've given us, in this case, they gave us the nu, the frequency, in a unit called hertz. So that unit called hertz is what we're going to use wavelength. So we'd like to get the wavelength in this, which is lambda, right? We divide each side by the frequency that they gave us, 9.75 times 10 to the 8th power, right? We end up with a unit in meters because we're solving for length now, right? So 0.308 meters, or if you prefer, 3.08 times 10 to the minus 1. It also asks what form of energy would this be? So we could look on the electromagnetic spectrum. We could take a peek back at that. Right, electromagnetic spectrum, we got an answer in the 10 to the minus 1 range for wavelength, or a frequency of 10 to the 8. So 10 to the 8 in frequency. Let's clean this up here a little. 10 to the 8, frequency is down here. 10 to the 8, look at that, folks. Draw a dotted line up, dot, 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 dot. That is closest to microwave. So what we would say is when we go to answer this, it has a frequency close to microwave, right? So it would be representative of microwave form of energy. So that guy here, we could say microwave here. Okay. So we know we have something representative of microwave frequency. Let's take a look at the other example then. Okay, so the second example, now we know that we have a wavelength and we're solving for frequency, which is nu. So we have lambda, we're solving for nu, speed of light, lambda nu. Right, divide each side by lambda, right, or the wavelength they gave us, that'll cancel out that value. We'll be left with the frequency then, 4.36 times 10 to the 19 hertz. So pretty high frequency form of wave. We'll look that up so we can determine on the spectrum what we think it may be. So let's go ahead and do that. So something in the 10 to the 19 order of magnitude. 10 to the 19. When I look at the scale on the actual list that we have here, 10 to the 19 falls right between here, dotted line up, right in between gamma ray and X-ray. So maybe that's how we're going to answer this. It's in between gamma ray and X-ray energy. So in that particular case, very high frequency, very high energy form, rather short waves as a result. So that kind of wraps up our review on how do we do C equals lambda nu. So till the next time, I hope you found this useful. Have a great day, folks.